Our sun is always flooding the earth with energy, even in a cold, frosty day. An object at a right angle to the sun's rays is receiving approximately 1000 joules of energy per second per square meter. That means that each square meter receives power at the rate of 1000 watts, which is a lot of power. If we can catch all or some of this, we can solve the issues of greenhouse gases significantly. A solar cell is used to harness the energy of the sun and convert it directly to electricity. Solar cell is also called photoelectric or photovoltaic cell, since it operates based on the photovoltaic effect. The modern photovoltaic cell consists primarily of silicon atoms. An atom of silicon has 14 protons, and of its 14 electrons, 2 fill the first shell, 8 fill the second shell, leaving 4 for the third shell. These 4 outer electrons are called the valence electrons. They are important because they are involved with interactions with other atoms, as in the case of the chemical bonds. But ordinarily, silicon will not help us capture and use the energy of the photons coming from the sun. We will need 2 other elements that are close in their electronic structure to silicon. The first is boron, which has 5 protons and 5 electrons, 2 filling the first shell, leaving 3 valence electrons in the outer second shell, which is 1 less than the number of electrons in silicon's outer shell. The second is phosphorus, with an atomic number of 15, which has 5 electrons in the valence shell, so it has 1 electron more than the silicon's outer shell's electrons. In a silicon crystal, each atom bonds with 4 neighboring atoms in a tetrahedral pattern. For our discussion, we will simplify the presentation of the silicon crystal. We will present a 3-dimensional crystal flattened to 2 dimensions. Each silicon atom with its 4 valence electrons shown is bonded to 4 other atoms. If we view our flat crystal along the edge, we see what appears to be a simple row of silicon atoms. Pairs of valence electrons form the covalent bonds between the atoms, and collectively they form the valence band. Unoccupied atomic orbits with higher energy merge to form the conduction band. These 2 regions are separated in energy, much like the regions between the allowed orbits in the Bohr model of the atom. This energy difference is called the band gap and refers to the energy interval where no electron is stable. When shining light on the silicon crystal, if the incoming photon's energy is insufficient, the electrons will stay in the valence band. However, if a photon of light has insufficient energy, a valence electron can absorb the photon, jumping into the conduction band. When sunlight strikes the silicon crystal, the photons are absorbed by the valence electrons, promoting them to the higher energy conduction band. And if electrons are in the conduction band, they are free to move and therefore can carry an electric current. Note that the crystal is still overall electrically neutral. However, electrons, once promoted, can spontaneously fall back into the hole in a process called recombination and emit energy in the form of photons. If we are to use the energy of the electrons now promoted to the conduction band to power our electrical devices, we must first separate the electrons from the holes before they can recombine. This can be accomplished with an electrical field. A modern solar cell incorporates an intrinsic electrical field that will separate the charges, giving us the current we need. This electrical field is created by a p-n junction in a modern solar cell. Doping is a process where small numbers of impurity atoms replace some of the silicon atoms in the crystal. One can make n-type silicon by adding impurities such as phosphorus with 5 electrons, 1 more than silicon. When in the crystal, 4 of its valence electrons form complete bonds with neighboring silicon atoms. This leaves 1 extra valence electron that will orbit the phosphorus atom in the Bohr-like orbit at a very low temperature, but will diffuse through the crystal at ordinary temperatures. A phosphorus atom is called an electron donor because it donates 1 extra electron to the silicon crystal. Because the phosphorus atom has 1 more proton than silicon, it has a net positive charge. One can make p-type silicon by adding impurities such as boron with only 3 valence electrons. It forms only 3 complete bonds with the neighboring silicon atoms, leaving 1 incomplete bond which has the ability to catch an electron, using a nearby electron from the valence band. This neighboring electron leaves behind a positive hole that can diffuse through crystal at ordinary temperatures. With an extra electron near the boron, the region has a net negative charge, and because of this, the boron is called an electron acceptor. A p-type and an n-type silicon in contact with one another form what is called a p-n junction. Electrons from the n side diffuse across the p-n junction to the p side, and holes from the p side diffuse to the n side. This time, however, before the hole and the electron can recombine to emit a proton, they are separated by the electric field created by the p-n junction. The negative electrons move to the positive region, and the positive holes migrate to the negative region. Therefore, by separating the electrons from the holes, we have prevented their spontaneous recombination and loss of their excitation energy. Now we have all of the pieces required to construct a solar cell. We start with the electrical layer, which serves as an electrical contact and as a substrate to support the rest of the cell, which is often called a back electrode. A thin wafer of boron-doped p-type silicon is laid down. Phosphorus is then diffused into the top surface, forming a p-n junction very near the top. With the p-n junction near the top, most of the sunlight will easily reach the junction. An anti-reflective coating is spread onto the front surface to cut down on reflected light. Finally, front surface contacts are made to collect the electrons arriving from the junction. The grid is constructed with as few contacts as possible so that the p-n junction is not shadowed too much. We can now power a light bulb or an electric motor by completing the circuit. Now the cell is complete. Photons of sunlight pass through the thin n layer. In the junction, the energy can be absorbed by the electrons and excited to the conduction band, leaving behind positive holes. But before these can recombine, the electrical field in the p-n junction separates themselves. The electrons move forward to the front surface and the holes move towards the back. They then travel through the load and around to the bottom of the solar cell. The number of the electrons that leave to the front contact is equal to the number of the electrons that return to the back contact, where they recombine with the holes. As more photons of sunlight are absorbed, electrons are excited into the conduction band and the process is repeated. No electrons are used up in this process. Photons give up their energy to create electron-hole pairs. The electrons give up their energy in the form of an electrical power and return to the contact of the cell, where they finally recombine with the positive holes. It is simply the conversion of energy, and the silicon solar cell should work, in principle, indefinitely. With no mechanical parts to break down, solar cells have operated in practice for 25 years and more. The energy conversion efficiency of a solar cell is calculated by dividing the electrical power a solar cell produces by the sunlight power it receives. The efficiency of solar cells can range from 6% if silicon is amorphous to 40.7% if multiple junctions are used in research laboratories. However, the practical solar cells currently in the market are about 14 to 19% efficient. The reason for a lack of high-efficiency solar cells in the market is the cost associated with them, since expensive materials such as gallium arsenide are used to fabricate them in the laboratories, and they can cost up to 100 times the cost of low-efficiency amorphous silicon cells. One of the methods to increase the efficiency of solar cells is to increase the intensity of light that is projected on the cells by using concentrator systems, which result in generation of higher numbers of carriers and therefore higher current. This method can increase the efficiency of solar cells by up to 15%, but these systems are still not cost effective enough. The cost per delivered kilowatt hour is commonly used to compare the cost of the electricity generators. The amount of irradiation and the efficiency of the solar cells are two factors affecting the overall cost of solar generators. The cost of delivered energy ranged from about 60 cents US per kilowatt hour in regions of low solar irradiation down to 25 cents US per kilowatt hour in regions of higher solar irradiation as of 2005. As a comparison, retail electric costs range from 4 cents to 50 cents per kilowatt hour worldwide as of 2005. We must also take into consideration the useful life of solar systems when analyzing the cost per deliverable power. Most of commercially available solar panels have a warranty of 25 years and are expected to have even longer lifespans. The energy payback time is another method to examine the feasibility of electricity generating systems, which refers to the recovery time that is required for generating the energy that was spent when manufacturing a solar panel. For modern solar modules, the energy payback time typically ranges from 1 to 4 years, which depends on the location and the solar module type. For example, crystalline silicon solar cells have energy payback periods of 1 to 2 years, while thin film solar cells' energy payback period is less than 1 year, although the conversion efficiency is lower than conventional solar panels. As a net, solar panels produce much more energy over their lifespan of 20 to 30 years than the required energy to manufacture them. In general, solar panels are economically beneficial if considered over their lifespan of 20 to 30 years.